are variation of some of the algorithmic techniques. Okay, so in the divide and conquer, what we have, first you divide the problem into subproblems, and second step is you solve each subproblem separately. And third step, of course, it's not part of the title, you merge them. Merge the solutions of the subproblems to get the solution to the original problem. Okay, so this author who proposed this ultimate convex algorithm, Kirkpatrick Seidel, okay, so he given a fancy name, okay, so marriage before conquest. So here, yeah, first step is same, we divide, and here these two steps are changes actually. So here the med step comes before, not exactly med step, okay, somewhat med step, and then you solve the subproblems later. Okay. So this will go about this conventional algorithm. Okay. So we want to have a algorithm which takes order n log h time, where n is the number of inputs and h is the number of outputs. So what we have actually, we have points in two-dimensional plane. So we take their x coordinates and find the x median of their x coordinates. So let's call them as a actually x mid. So this basically this is the median of x coordinates. And yesterday we discussed that this can be done in linear time. Okay, so remove this one. Okay, and then so this may be this coordinate. This may be yeah, x median may be somewhere here. So in the divide and conquer, we used to solve the both the subproblems. Okay, but here we want to do the mid step. So in next step, what we have to do it actually is we have to find the upper tangent as well as lower tangent in the mid step. So here what we want to do is we want to find the upper tangent and lower tangent first before computing the or before solving both the subproblems. Okay, so so that is the we are doing the mid step before the solving subproblems. So here finding the upper tangent, upper bridge is same as lower bridge. We focus our attention to finding the upper bridge here. So somehow if you find this one, upper bridge between these two, okay, say in linear time, then what we can do is if you take this part, all the points here are not part of the convex upper hull. Okay, so you have to take the points which are this side, find the upper hull, and take the point this side, find the upper hull this side. So you do solve these problems recursively. So this is the idea here. So everybody understood this main idea? So once again, I'm repeating. Here we want to have a convex algorithm n log h time, where h is the number of vertices on the convex final output. But we don't know the size of value of h and size of the output, and it can be a constant or it can be a order n. Okay, anything is possible. So we want to do it in n log h time. Obviously, we cannot sort them. So without sorting, what we will do actually, we take their x coordinates, find their median. Okay, so x mid is this median, and line passing through this is say L here. Okay, and this divides the points into two halves, which are on the left side, which are right side. So if you look back and see this divide and conquer method, so we used to find the convex hull of the left half of the points and the right half of the points recursively in the same manner, and we used to find the upper tangent, lower tangent here. That is divide and conquer. But in this method, okay, uh, we find the upper tangent, lower tangent before solving both the subproblems. So finding the upper tangent is similar to this lower tangent. We'll focus our attention to finding the upper tangent. So assume that somehow we found this upper tangent, say linear time. Okay. So if this is the upper tangent, we can remove all the points which are below this upper tangent. Or in this paper, it calls the upper bridge. Okay. So if you remove this one and you take the point which are on the right side and find the remaining part of the upper hull for the left half of the points, and find the upper hull for the right half of the points. So do the recursion later. So this is the change in this strategy. So you are finding the mid step before solving the subproblems. Okay, clear? Any questions?
Excuse me, sir.
Yeah.
Sir, what if when we are removing all the points below the upper tangents, the point which are contributing to the lower tangent get removed?
Yes. So we are discussing only algorithm for finding the upper tangent. So similar procedure will be for the lower tangent also.
Okay, and both intersection has to be removed or union?
No. See, you assume that the two separate algorithms are running one after other. Finding upper hull is one, and finding a lower hull is another thing.
Oh, okay, yeah. Thank you,
Okay.
sir. Yes.
So here, uh, when you are talking about upper hull, there could be a vertex like this. The two vertices may be having a same x min and x max. So for lower hull, you have a something like this, and upper hull is something like this. So this vertical segment may be added to feed into that to complete this convex hull at the final stage. Okay, so that is not a crucial. Okay, that you can do it. Basically, find the x min and x max. If more than one coordinate or more than one point having the more than one point as the same x min coordinate, then you have to consider both of them. Okay, or topmost one for finding the upper tangent. Okay, and bottommost one for the finding lower tangent, and do it. So similarly, this side also, if you are having a more than one points with the same x max coordinate, take the topmost one as a part of the upper hull construction, and the bottommost point for the construct of the lower hull. So that slight okay, additional care you have to take. Okay, so algorithm is clear to everyone. Any questions?
Yes, sir, one doubt.
Yeah.
Sir, when you are removing the points in the middle, like you are considering the quadrilateral formed by top and bottom tangent, like
No. See, no. See, we are discussing only algorithm to find the upper hull. Okay, lower hull. similar algorithm will be there for finding lower hull. So basically, we have a two sub problem. One is finding upper hull and finding the lower hull. Both are same, symmetrically similar algorithms.
Sir, then can you just repeat how you are removing the points in the between which you have crossed out? Like, how are you removing those?
Okay. See, okay, I'm repeating. We have a n points given to us. Okay, and we want to find the convex hull of these n points. So what I'm doing, first I'll find the upper part of the convex hull, upper hull. So from here to here, only this part. Okay, once I find this one, I'll find the lower hull of these points. So finding the upper hull algorithm is similar to the lower hull algorithm. We discuss algorithm to find the upper hull. Is that clear to everyone?
Yes, sir. Okay.
Okay. So now we are discussing the algorithm to find the upper hull. Okay. Now find the x min, x max in the given point set. If there are more than one point which are having the same x min, then take the topmost point out of all of them. Means highest y coordinate. Similarly, if more than one point having the same x max, you take the topmost one among them. Okay. So you want to find the, basically you remove this part of the points from our computation process, since we are only computing the upper hull. Okay. Now algorithm for finding the upper hull is as follows. Find the median of x coordinates of these points. So let's call them as a x mid. Now take a vertical line passing through x mid. This is L. Now here, if you are following the traditional divide and conquer algorithm, we should find the left hull. That means convex hull of left sub points. Here this one, and convex hull of the right sub of the points. So once you have the convex hull of both of them, you find the tangents, upper tangent, lower tangent, like a divide and conquer strategy, and get the solution to the original problem, convex hull of all the points. So instead of doing this way, what we do actually is we find this upper tangent, the mid step, without finding the left hull and right hull. So assume that somehow we found this upper tangent or upper bridge in logarithm. What is upper bridge means? You have to find a points, one from the left side, another from the right side, so that actually this is the edge, okay, of the convex hull. Okay, assume that somehow we find this upper tangent in linear time. Then you take this rectangular box below this upper tangent. All the points can be removed because these points can't be part of the upper hull, upper part of the convex hull. Okay. So what we'll do actually, you can take the remaining points here and repeat the same procedure, find the remaining part of the upper hull, and take the points here, find the remaining part of the hull here. So this is the divide and conquer strategy. Is the algorithm is clear to everyone? Any questions? Okay. There's no any questions. Okay, let's look at this time complexity here. Now I'm representing the time complexity in terms of a input size as well as output size. So, so we are spending order and time for the mid step as well as okay divide step. The finding the median of x coordinates, okay, and dividing the problems into sub problems. Points on the left of this one and right of this one. Of course, you don't need to divide them as such, okay, but you can divide. So basically, we are finding the median in the divide strategy, that is linear time, and during the med step, that finding upper tangent takes a linear time. And what else we have? We have two sub problems. One is we have a n by 2 points. Okay, assume that left hull has a h1 edges. And second sub problem is you have n by 2 points on right side, and number of hull edges are h minus 1 minus h1. Okay, so here h is equal to h1 plus h2 plus 1. Here h is the number of edges or number of vertices. Okay, you are taking the number of edges here. So this is one edge, upper edge. So if you remove this one edge, so whatever left over is h minus 1 edges. So that is together h1 plus h2. Okay, is that clear? Now question is, we don't know the value of h1, okay, or if you assume this is h2, okay, we don't know the value of h2. So we don't know for what value h1 you will get a maximum here. So we have to do is actually we have to take a maximum possible value. So suppose for example in the divide and conquer strategy, okay, you are dividing the problem every time to equal parts, then h also h1 also h2 also becomes a h by 2. So if you are dividing the problem into two equal parts, of course we don't know if it is a, you have to find a equal number of edges on either side or not, we don't know. Okay, so one may be bigger than the other one. Okay, if you are in the divide and conquer strategy, if you are able to divide the problem into very skewed, only one side one is there, other side actually remaining all of them is there, then we get a skewed partitioning, so complexity may go up. Okay, in the case of quick sort, divide and conquer. Okay, so we don't know for when actually you will get a maximum. So when you are getting a maximum, when this case or one side is all the h minus 1, other side is only 1. We don't know. Okay, skewed partition. So we don't know what partitioning actually of the h. Okay, you will get a maximum, we don't know. So we'll take the maximum value of maximum, okay, for whatever value it gives a maximum, the h1. Okay, so you assume that if h is greater than 2, otherwise you can assume that order n, okay, if h is less than or equal to 2. So any question in the recurrence relation? So if the recurrence relation is clear to everyone,
Yes, sir.
now if you solve it, yeah. Yeah, tell me. Yeah, somebody asked question. No question? Okay. If everything is clear, we'll proceed. Basically, then you have to show this is actually or n log h. Can you show this one? If you solve this reconciliation, you'll get n log h. So we'll prove this by induction on h. So we assume that actually, okay, for induction h is equal to 2. What happened? This is the basis. This is the second part of this reconciliation. It's some constant c times of n. So this is okay, is less than or equal to c times of n log n is equal to 2. Oh, h is equal to 2. Yeah. So basically, this is actually, so basis is clear. Okay. Now you take inductive step. So this is equal to, okay, some constant times of n. Okay, first part of the calculation plus the maximum of h1. Okay, and what we have actually c times of, you have n by 2 log h1 plus c times of n by 2 log h minus 1 minus h1. So if you simplify this one, so what you will get, you can take out this cn by 2 here and take the max inside, and we can write this as a yes. So obviously this is less than or equal to, so this can be replaced with this one. So this will be the maximum only when it is divided equally. Otherwise, this value is always lesser. So now you simplify it. Okay, what you will get is actually, is it clear? Any questions?
No, sir.
Or not clear?
No questions, sir.
Okay. Okay. If it is clear to everyone, now only thing left out is actually is how to find the upper bridge, upper tangent. in linear time. Once that you are able to do it, then you have algorithm. Okay, so we'll discuss this algorithm here. So we have a n points are there, and we want to find the upper tangent with respect to this L, where this x mid. Okay. Now, as a first step, what we'll do, you pair these points. Okay. So you take any 2 points and pair them. This is one pair. Okay. There may be another pair. So there could be another pair like this. All sorts of. Okay. You are randomly pairing the points. Both the points may be left off or right off, doesn't matter. You just randomly pairing them. Of course, in the pair, actually, if you have a pair Pi, Pj, just keep the Pi as the leftmost point and Pj is rightmost point within the order. This x coordinate of Pi, okay, is less than or equal to x. You take this less than actually, okay, x coordinate of Pj. That's all. You keep that order. Okay, this is also not very important. Okay, if they are same, then use the y coordinate. Which one is below? You keep the first one, and the above one as the next one in the pair. Okay. So this is not a crucial. So we have a n by 2 pairs. Now what we will do? You find the lines passing through this thing. Basically, you find the slopes of these lines. So find the slopes of these n by 2 lines defined by this n by 2 pairs. Okay. Now take the median of all these slopes. So let's this is a assume that this is a say no, I should not use a j. Okay. Uh, okay, I use the s for the slope and m for the median. Sm. Yeah, you will understand what is the purpose of the taking the median of the slopes. Okay, once we have this median, now you partition these lines or these pairs into 3 categories. All the pairs which are having the slope less than the median slope, and all the slopes which are having equal to this median of the slope, and all the points, okay, which are having the greater slope. So you divide these pairs. You have n by 2 pairs. We divide these pairs into 3 groups. Okay, all the pairs which are having the slope less than this median slope and equal to median slope and greater than the median slope. Okay. So everything look it's very uncertain things like that. Just 1 or 2 steps, everything become a clear. Why we are doing all these things. The idea here is, so if you want to have a linear time algorithm, I told you yesterday, so we need a reconciliation, something like this. So you want to remove a fraction of input, say 1/4 you remove it, in linear time. So you are searching for the upper bridge. In every iteration, you are taking the linear time and reducing your set space by 1/4. The remaining 3/4 set space is there. And if you can do this one, so you will get an order and time algorithm. So to get rid of 1/4 or a fraction of input, we are doing all these things. Okay. Okay. For that, actually, the median is helping us. Okay. That that it becomes clear just in a couple of minutes. Now, so you have the median slope. Okay. Assume that actually the median slope is say this one. This is the slope of the median. Okay. So maybe that slope may be occurred maybe with respect to this particular pair. This particular pair may be giving the slope SM. Okay. But doesn't matter. With this slope, you draw a supporting lines to each of these points. You take all these lines with the median slope. So what we are doing, we are taking the median slope, okay, and we are drawing a line through each point with that slope. So these are the lines. Now, out of all the lines, you identify this line, okay? I mean, topmost line here. So this line actually is the supporting line to the final convex hull. Okay, once again, I'm repeating it. We have an endpoints. Our aim is to find this upper tangent here. This red line, whatever indicated here, this is what we want to find. For finding that one, what we are doing actually is we pair the endpoints into n/2 pairs in the first step. Okay, so find the slopes of these n/2 lines defined by these pairs and take the median of these n/2 lines. Okay.
Sir, what exactly do you mean
And
when you say median of lines?
what is the median of n numbers actually?
The number falling in the
The slope is
middle when you
slope
sort it.
is some value. Yeah, slope is some value. So you have a n/2 slopes are there. Okay, n/2 values are
Okay,
there. What is
so
the
median with
meaning of
respect
n/2?
slope. Okay, okay. Understood.
Yeah, median of the slopes.
Okay.
Okay. Yeah, maybe lines is what is indicated here wrong. Okay. Okay. So we are finding the median of this n/2 slopes. Now you divide these pairs into three groups. All the pairs whose slope is less than the median slope, the first one. Okay, this one. And all these pairs whose slope is equal to this median slope, and all the pairs whose slope is greater than the median slope. Okay. Now, in next step, what we are looking at actually is, yeah, here. So we are drawing a lines parallel to the median slope through each of these endpoints, and we are identifying the one, okay, which is the topmost one. See, there could be a point something like this also, which may be above this point. There could be a point here which may be above this one, but we are not interested about that point. We are only finding a supporting line to this convex hull, which is parallel to this median slope. There could be any number of points which are above this one. But we are finding this particular this thing here. Is that clear? Suppose this is what you call a supporting line. Okay. Basically, it is a tangent to this final convex axis. One of the tangent. This may not be a defined edge, but it is a tangent to the final convex polygon. Okay. Now, so take the case scenario. This supporting line, which is parallel to this median slope, it can have any number of points here possible. If it is points contain some from the left side, some from the right side, then this is our upper bridge, upper tangent, so which are defined by these 2 points. Okay, then in that case, our the procedure terminates. That is the result. Another possibility is this is the line that which is actually is the middle of this x median. Okay, now you have a point here. So this line, supporting line, may be having a point only from the left side. Okay, another possibility is it may be having a point which may be passing to the point on the right side. Three possibilities. If you got the first case, then we are done. Okay, so if you are getting a second case where this supporting line only having a point from the left of it, that point left side, this L. Of course, there can be more than one also, but all the points are on the left side. Here also there can be more than one, but all of them are from the right of this median line. Okay, now we will discuss this one, this middle case where these points are from the left off. Okay, now the slope of this line is Sm. Okay, so we have a n by 2 pairs, out of which, okay, so there are half of them whose slope is greater than this one. This is the set S3. Now you consider all the lines, all the pairs whose slope is greater than Sm. Okay, so certainly these points, the bottommost point cannot define upper bridge. Yes. Yes or no?
Yes, sir.
Yes, everybody should convince about this one. The slope of this supporting line is equal to Sm. And now consider the pairs whose slope is greater than Sm. Okay, here I taken 3 examples. Okay, so here these points which are indicated by the circle can't be part of the upper tangent. Suppose if you take a slope which is equal to this one, that is the set 2. So now you take a, now let's take a line which is parallel to this one. Either here or here or here, whatever, anywhere you take. So here, these 3 lines and this point also can't be part of the upper hull. So we remove these points. Okay. So how many points we removed? 1 point each from this set S2 and S3. How many will be there? At least half of the number of pairs. That means n by 4. So that is what we are getting here. So we are removing 1/4 of the points and we are considering the remaining points and we are repeating the same thing to find the upper hull. Yes, is it clear? So I'll repeat once again. So our aim is to find the upper tangent. And what is given to us? Given to us, okay, that line which divides this and next mid. These values will be known to us. So what we do? We pair these points, n points into n by 2 pairs in arbitrary order. Okay, and find the slopes of these n by 2 lines. Find the median of these n by 2 slopes. And using this median slope, you divide these pairs into 3 groups. All the pairs whose slope is less than the median slope, all the slopes are equal to the median slope, all the slopes whose slope is greater than the median slope. Okay, then what you do? You know this median slope. Okay, with the median slope, you draw a line through each of this. Now, drawing means no need to draw actually. So I'm pictorially I'm representing. You take a line through each of these points with this median slope. So these are the parallel lines. What you see here. Out of all the parallel lines here, you take the topmost one. That means this one. Okay, this particular line. All other lines are below this one. So this line is a supporting line to the convex polygon, final convex polygon, or a tangent. So this tangent may be passing through a vertex or it may be passing through edge of the convex hull, final convex hull, but it is a tangent. Okay. Now look at this tangent or supporting line, and what we have actually 3 different possibilities. The first possibility is this tangent may be having some points from the left of, the point left of L, some points right of the L. If that is the case, and this point defines the upper bridge, upper tangent, so we return this as a output of this procedure. Okay, done. If that is not the case, now you take the second case. So this supporting line here having some points which are on the only left of this L. In that case, what we will do actually, you look at this lines, okay, whose slope is, or pairs whose slope is greater than this SM. So for example, this, here, this. I've taken a few examples. Oh, these are parallel actually. Okay, these three actually. This. Out of all the three pairs, these 3 points can't be part of the upper tangent. The leftmost point out of this pair. Okay. Now you take these pairs whose slope is equivalent to SM. In this case also, leftmost point can't define the upper tangent. We remove them. So how many points we remove? At least n by 4. So once you remove the n by 4 points from the input set, whatever left over is 3n by 4. And how much time you spend to do all these things? Linear time. Okay. The pairing points, finding the slopes, taking the median, and dividing them into 3 sets. Okay. And finding the supporting line with SM, all of them take a linear time. And removing these n by 4 points, okay, you take each pair, the slope is greater than this one, and remove the leftmost point. If it is equal to the slope, then remove the leftmost point. If it is the slope is less than this one SM, then do nothing. You keep the both of them. Okay. So this is the procedure. So this is the reconciliation, and you will get order and time to solve this upper tangent. Same thing happens for in this case also. Okay. So in this case, what you have to do is third case. Now you take the slopes which are less than this one. These type of distance. So here the case is, you know, all the points which are belongs to this height of L. Okay. Here this line, supporting line with slope equal to this median slope. All of them having a from one side. So in this case, you consider the pairs whose slope is less than this one and remove these points here. If it is a parallel, then remove this point. So in this case also you can remove n by 4 point, at least n by 4 points. Okay, this is the algorithm. Now you might be understood why you have to take the median. Why you have to take the median of these slopes? Why? Because see, we are able to ensure 1/4 of the points are removed, a fraction of the points. So if you take size of these two, okay, this will be at least n by 4. Or if you take these two, the size is at least n by 4. Okay, so taking the median actually helps to guarantee that, okay, a fraction that n by 4 points can be removed in linear time from our set space. Okay, so is it clear to everyone? Any questions? Of course, you have to think once again all these things, whatever I told. This algorithm, if you search on the Google, you will find a original paper and some lecture notes in some university where it's written very nicely. Okay, and you can also see some short okay web page also algorithm actually. So whatever I worked out actually from the paper, and this is the my version of the algorithm. Okay, is that clear?
Yes, sir. Sir, what will be the name of the paper or like to search?
See, ultimate convex algorithm. You search by ultimate convex algorithm, you will get this links. Yeah, first 3 links you see actually, you will get actually this.
Okay, sir.
So only problem here is we are finding the median again and again. In last class I told, okay, the constant involved in the finding the median is very large. So that makes this algorithm inefficient. Asymptotically, this is a very good time complexity. See, original paper. This paper is appeared in '86 in actually Sam Journal of Computing, February '86. Okay, and later, okay, nearly after 10 years in '96. So there is another algorithm by Timothy Chan. That also takes h time, but here it does not use a median algorithm, and that I'll discuss in the next class on the Wednesday, and which is a beautiful algorithm. It uses simple strategy: divide and conquer and gift wrapping, plus finding a tangent in logarithmic time. These three, okay, and very simple and very elegant algorithm, very easy to understand. That I'll discuss on the Wednesday class. So another thing what I want to say, okay, is Timothy Chan is a very good researcher in computational geometry, one of the best. Okay, all his papers are very simple, very easy. Okay, but results are very strong results. So he was actually Waterloo University in the Canada. I don't know now he's still there or he moved from there. I don't know. Okay, so you can look at any of his papers. They are very good, and algorithm will be simple and will show in analysis. Actually, everything is in the analysis. Okay, we'll discuss this on Wednesday. And regarding this, okay, regarding this weightage and all those things also I'll discuss on Wednesday. We will have a time on that day. Okay. Okay. See you. And please go through this algorithm and try to understand. What we learned here is one is a variation of divide and conquer. Say what is called as a marriage before conquest. Okay. Where is that written? Yeah. And second thing is this one strategy. Another strategy is how we found this bridge. Okay. Every time we are removing the fraction of input, this is called a prune and search technique. You prune the input and search in the pruned input. Okay. These are the two techniques. Okay. So we'll continue on next Wednesday.